Okay, Thanks very much for the introduction. Yes, I'm Tim Dijkstra here to talk about digital twins for data centers, and I'll give you a quick overview of who I am, why I'm here. So I did a PhD in mixture of high performance computing, astronomy, and computer graphics, and Portsmouth in the UK. And following my PhD, I joined the Cray supercomputing company in 2017, which of course became part of Hewlett Packard Enterprise a couple of years later, where I now work as a senior research engineer. I'm in the HPC and AI EMEA Research Lab, which is part of Hewlett Packard Labs, and I work on a variety of different activities, internal research projects, collaboration centers with customers, and procurements and other types of things. A picture of me here at the Shark Rock Pier, just over on the seafront there, so worth a visit if you get the chance while you're here. So I'm part of Hewlett Packard Labs. This is essentially the research arm of HPE. HPE is a big company, 60,000+ employees, and the group we're in focuses on what comes next. So advanced development, trying to understand immediate customer issues, influence product roadmaps. We don't tend to work directly on product, but on things to come, and sort of building cutting edge operational proof of concepts, applied research, and exploratory research. So looking at the horizon, future technologies, and this type of thing. Within Hewlett Packard Labs, which is one of the older research organizations, we're the EMEA Research Lab. And so we focus on sort of deep technical collaborations in the EMEA region, focusing mostly on supercomputing and AI. And so just a couple of the things we're interested in here. I won't spend much time on that, and you'll hear a little bit more about it in the keynote this afternoon, where my manager Utz will talk about some of the research that we do. But I'd like to focus this morning on digital twins, and it was nice to hear Mr. Hero in the keynote talking about this blurring of the lines between the physical and the digital, which I think digital twins are a really good example of. So in terms of what a digital twin is, it's a set of virtual information constructs that mimic the structure, context, and behavior of a physical asset that may be dynamically updated with data from the physical twin throughout its life cycle, with the aim to inform decisions that realize value. So really, we have a digital representation of some type of physical asset, and we try to use that representation to realize some value, to help us understand what we can and can't do, or what we should and shouldn't do surrounding that physical asset that we care about. And digital twins in general, the scope of one may be limited to any or all of these different levels. So you have sort of at the lowest level a descriptive twin, where you simply have a physically accurate, realistic representation of an asset, facility, or product. Essentially looking at CAD data, for example, could be counted as a descriptive twin. Then moving up from that, we add more and more to our twin to make it more detailed, provide us higher value. At level 2, we have this informative twin, where you integrate some real-time data to provide insights into the performance of your object of study. Going up from that, you have a predictive twin, where you might leverage that data to predict the outcomes and problems for the operation of that facility or asset. And then we build further into a comprehensive twin, where we might use advanced modeling, computational simulation, to do predictions, prescriptive analytics, this type of thing. And then even higher to what we call an autonomous twin, where we might be using real-time data feeds to learn and make decisions automatically, where the twin is really able to control its physical counterpart automatically. So the higher the level you go, the more value this digital twin might be able to realize. And so these are the different labels we've added for the things you might add to your model to get between these levels. Everyone in? This was the key slide, so I have to be careful as I skip that we don't kill it again. Okay, very good. We've made it past the key point there. So what I was saying is that, I described a bit about digital twins, what they are, what we how we extract value using them for generic physical assets of some kind. But the talk really is about digital twins for data centers. And the first question is, well, why exactly do we care about energy efficiency and sustainability for our data centers? And so, I mean, perhaps preaching to the choir a little bit here, but you know, we're trying to achieve net zero emissions. This is one of the goals of HPE in particular, and they have quite a extensive portfolio of initiatives to increase our sustainability of the operations and the machines that we create. And we see that the International Energy Agency has predicted that, you know, I think in 2022, global energy usage attributed to data centers was about 500 terawatt hours-ish. And in the worst case, they believe this could double by 2026. And, you know, we can see what just 1 terawatt hour of power really does. I mean, we could be powering 70,000 homes, lighting 1 million homes, cooling 500,000 homes for an entire year. So really, the amount of energy that our data centers are using globally, I mean, it's 2% of global energy usage, and it really is something that we need to care about. Taking as an example, Frontier, one of our larger installations out in the US, you know, it's a 1 exaflop plus machine, and peak power is 28 megawatts. So that's really, you know, a huge amount of power. We've got a lot of high density, high power components in here, almost 40,000 GPUs, 60 million plus parts. And so, you know, we've built an incredibly powerful machine here. But of course, with great power comes great responsibility, as our good friend Uncle Ben said. We're very confident in the value that to society that our research and development enabled by this machine and these machines in general bring. But we do have to be cognizant of the environmental impact, both of building the machine itself and also running the machine for the duration of its life and subsequent decommission. And HPE has a bunch of sustainability initiatives, you know, supply chain focused, etc. But I'm not really here to talk about that. What I'd like to focus on is what we can do once we've built the machine and started operating it. How can we optimize the operation of that machine? And one of the ways we can do that is via digital twins. So in general, where can our data centers be optimized? We have, you know, the initial configuration of the system, trying to ensure that you're not underutilizing, you're not over provisioning, you need to balance your resources. So there's configuration concerns, the environmental impacts of the cooling of your machine, you know, overcooling, poor airflow, etc. Thermal analysis, these type of topics contribute to the efficiency of your data center and areas for optimization, user behavior on the machines, how they consume their resources, when they consume their resources, and operational efficiency. So in general, you know, real-time analysis, performance visibility, actually understanding our data center, how it's operating, and where there are opportunities for improvement. This is where we think a digital twin can help. So in general, digital twins have quite a few different use cases, and we're focusing on really just a few of those. Diagnosing network congestion, predicting cooling requirements, optimizing job scheduling. These digital twins can enable us to answer complex what-if scenarios. Imagine if you could predict the impact of a pump failure before it happens. This type of thing really does contribute to the operating efficiency of our data centers and essentially to the overall total cost, right? So we're interested in many different kinds of use cases with our digital twin, but we focus a little bit more in this talk on insights from visualization and workload scheduling. So I have a quick snapshot of some, if I skip through the animations, some sustainability and digital twin research at HPE. If you're looking for a readily available product, there's things like the Cadence Data Center Insights, which we do supply. But we focus more on this exadigit project, which is something I'm going to talk a little bit more about. But there's other things like digital twins of the Earth, lots of metering and sort of things that or initiatives that we have at HPE to help in understanding our systems as well as we can. So the XDigit project is essentially a digital twin consortium for supercomputing. We're aiming to build an open source community for comprehensive modeling of supercomputers. A bunch of different partners that are involved here. A large collaboration with Oak Ridge, and so you'll see Oak Ridge logo on a few of these slides. And so mostly folks that have EX systems, but we're not aiming just at EX systems. So the aim is for wider supercomputing systems to be supported. And you see here in terms of our working groups, the type of things we're looking at. So we have groups that are focused on the different areas that we're interested in for a digital twin. So application fingerprinting, trying to understand which applications are running on our system, how they're running, and how we can optimize that. AI, MLRL, so how do we use sort of advanced data analytics techniques to understand and predict behavior. Visual analytics, how do we look at the system? How do we understand the sort of complex data that we're extracting from these massive machines? Power and cooling, network, and validation, and uncertainty quantification. So these are the different areas that we've split the work related to our digital twin in, with some overall looks at architectures and docs, etc. And we end up with an architecture that looks a bit like this. So you see, we split into the central energy plant and the supercomputer. On the central energy plant side, we have a cooling model that's really aimed at replicating or simulating the behavior of your cooling system. And this provides an input to a resource allocator and power simulator that's on the supercomputer side. These will link together by telemetry and viewable through a visual analytics sort of platform. That could be dashboard, it could be VR, augmented reality. And then this is still a work in progress, so just how we integrate the work going on the network side and application fingerprinting into the overall architecture, we're still working on. And then we have a feedback mechanism to our physical twin, which is the real system. I'd like to talk about some of the work that we particularly have been involved in at HPE. So one of those pieces of work is workload management simulation. So we had a student who coded up a Slurm simulator for us, where we could use past data from some of our supercomputing systems with customers that we work with, Archer 2, Lumi, some of these large systems in Europe, so that we could predict the impact of scheduler configuration changes. So, but with a particular focus on power management, our student Alex was able to provide some insights on how things like CPU frequency changes would impact your job runtime, how your scheduling firstly, the scheduling simulation itself was reasonably accurate, matching against the real data, and he could accurately match that across different quality of service charges. But we could also, that's interesting. Unfortunately, the content from this table has disappeared, but one of the other pieces of work he did as part of this was use this simulator to try to predict what would happen if we shifted power usage outside of the peak hours of power utilization for the data center. So he adjusted the Slurm configuration to shift job scheduling so that drain times were during peak hours and extra large jobs were run overnight, and managed to shift power usage outside of this 11 a.m. to 4 p.m. peak period with really not much impact on users. Unfortunately, the interesting graph has dropped out of the slide for some reason. Well, I can we have the paper and I can show you afterwards. So here we go. In terms of interfacing with our digital twin, there's 3 different types of interface. We have a nice augmented reality interface for visual analytics, a console interface for development, and a web-based dashboard interface for HPC engineers to use to really see metrics in real time and played back historically. So For a complex system like Frontier, which is the one that you see here, we really found that augmented reality with dashboards is quite an effective way of providing timely visual insights into the system. So navigating a complex system like this really was improved by, maybe perhaps more novel interaction methods such as augmented reality. In terms of visual analytics, which is something that we've been assisting with at HPE, we're using the Unreal Engine, which is originally a games engine, but you can use it for these types of digital twin softwares. And you just see a couple of pictures of some of the type of work we've been doing, which is loading these systems into Unreal, configuring them. You see a few different systems here. So you've got Frontier in the top left with the full cooling pipe work. But we have, Cetonics, which is the Pawsey system out in Australia in the bottom left, and Lumi, the large supercomputing system in Europe on the bottom right, and a couple of the different types of visualizations we've been working on, like network connectivity up in the middle. So still a lot of ongoing work on the visualization side. In particular, visualizing workloads is something that we're very interested in. So understanding your system load, power utilization, job distribution, see things like how your jobs are overlapped, where there's congestion, etc. Being able to visualize this is a really useful way of intuitively understanding some quite complex data. And we show an early interface that we've been using on our EX systems, which is a command line based viewer. And you see each of these gray tabs is essentially a cabinet, and you see a bunch of cabinets lined up with different jobs represented by characters. This is one of the early interfaces. We're currently working on a 3D version that overlays this on the models that we were looking at in the previous slide. And so let's just bring all this up. So one of the more recent parts of the Exadigit project is trying to generalize that to different systems. So a lot of the work I showed there was Frontier-based, but we've been working quite hard to allow folks to build digital twins of their own supercomputer based on all of the work that's been going on in this project. So being able to specify the layout of your system via a JSON, set of JSON input files, plug and play telemetry data loaders, so you can get telemetry from your own system, which is of course going to be formatted somewhat differently than for someone else's system, and creating cooling models for your own data center. So far we've got Lumi, Cetonics, Fugaku, Marconi, and Lassen, but we're working on others as well. And really the challenges we see here are firstly heterogeneity, so everyone's system looks a little bit different. Even if they're EXs, they often have different types of hardware in the cabinets, perhaps different numbers of hardware in the cabinets, and the data center around them is inevitably going to be a bit different. So building a model of the cooling system and power is always a little bit difficult as you move between systems. But what I'd like to quickly show is a video so you get an idea of what exactly this. So yes, just one final thing to show on a related topic is this initiative we've been working on. We're currently calling miniature physical twins. So we built what we're calling the Micro EX, a 1/20th scale model of our EX4000 system. We filled with Raspberry Pis. So you see in at the top the closed cabinets, 4 cabinets here. At the bottom, these are the cabinets open. In each cabinet, we have 4 Raspberry Pi Zeros. So each of these is just a small device, 4-core, and 3 compute cabinets, so 12 Raspberry Pis, Pi Zeros with a management cabinet on the right that has a larger Pi 4B. This gives us about 144 gigaflops of theoretical peak, which these days isn't very much. If you were to put that on the very first top 500 list, it would be at the top. But yeah, so far we achieved about 75. We haven't done a lot of optimization. I reckon we can get closer to that theoretical peak. But this is still probably 100 times slower than your smartphone, for example. But we have a full HPC stack on this. So, software management via CMU, modules, Slurm. You have MPI and via MPitch or OpenMPI, so you can run real supercomputing jobs that are just scaled down to a small size. We have Jupyter Hub, distributed PyTorch, and TensorFlow on there, so you can run small AI models. And really, the initial focus of this project was outreach and education. We wanted to be able to show people what our systems look like if they weren't able to go and visit a data center and see one in person. Take it to schools and places like this where you can let students play around with it and have an interaction with what looks like the real system, but you don't have to dedicate resources from your expensive system to enable this to happen. Although we have found that since showing it off, we're getting quite a lot of customer and internal interest in use of these for experimentation. Things like trying out Slurm configuration changes and seeing how they affect the queue and the jobs without having to play around in your production system. So there's been more interest than we were expecting, actually. And just final, a couple extra pictures of that. So we have put it next to a full-size cabinet for scale. And we've been building non-functional visual models just to display if you don't have the power or someone nearby to run the infrastructure. Then we also have these visual-only models, which you'll see this bottom right one at CI UK this week. Or you won't because you're here, but folks will. So yes, thanks very much for listening. Work we covered here was from a variety of collaborators within HPE and outside, particularly Oak Ridge. Bunch of papers of relevant work that's come through this Exadigit project. Feel free to reach out to me. This is a open collaboration, so if it's something you're interested in, reach out. You're welcome to join, and we have monthly calls, etc., etc. So yes, thanks very much for listening. Any questions? Happy to talk now, or you can find us after if we're running a bit short on time.